Welcome again to the class. As far as the yesterday's concepts were concerned, what we discussed yesterday was about the moment of inertia. Yesterday we gave the definition of the moment of inertia, and we know as far as the moment of inertia is concerned, the moment of inertia I about x-axis, we write Ixxr or simply Ix is equal integral of y square dA. Okay, and we write moment of inertia about y-axis of any plane area is equal integral x square dA. Before we go ahead in understanding or in using these equations, what's very important for us to understand one more important concept, that's what we call as the parallel axis theorem. As far as the parallel axis theorem is concerned, what the parallel axis theorem for the moment of inertia states. It says like we have uh, let's suppose we have any plane area, okay, and its area is, say for example, A, and we are asked to calculate the moment of inertia of this plane area about x-axis, or say for example about y-axis. Let's consider this to be our x-axis, and let's suppose this is our y-axis. We have to find the moment of inertia about x-axis, or we have to find it about y-axis. Now what we do, the procedure is, first of all we have to locate a small area element. Let's suppose the area element is having area dA, and we say that this area element is at a distance x, or we do it, this area that we have selected, this area will be having its own centroid somewhere. Let's suppose this is the centroid. Let's suppose the centroid of this area is at this point, what we call as centroid C, and let's suppose this is our origin. We know if we are asked to calculate the moment of inertia about, if we are asked to calculate the moment of inertia about this x-axis or about y-axis, we simply take a small area element. We take a small area element and see, draw the distances of the small area element from the x and y axis. The centroid of the small area element is to be selected, and we say, let's suppose this distance is x and this distance is y. Okay, then we have the definition for finding the moment of inertia about x-axis and y-axis. Now let's suppose we are asked to find the moment of inertia not about the x and y axis, but we have been asked to calculate the moment of inertia about an axis passing through the centroid. Moment of inertia about the centroidal x-axis and the centroidal y-axis. Okay, that is, if we are asked to calculate the moment of inertia not about y-axis or this x-axis, but we have to calculate the moment of inertia about an y-axis which is passing through a centroid and x-axis which is passing through the centroid. That is, we have to calculate the moment of inertia about the centroidal x-axis and the centroidal y-axis. Now what we will do, how we will find the moment of inertia about the centroidal x-axis and the centroidal y-axis. We will use the same definitions that we have discussed yesterday, but the thing is, the same definitions will be used. That is, yesterday we have discussed finding the moment of inertia about x-axis and y-axis. Now suppose this area is having centroid at point C, and we are asked to calculate the moment of inertia about an x-axis which is passing through the centroid. This is called the centroidal x-axis, and about a y-axis which is called the centroidal y-axis. Okay, how we will do it? This is very important. In order to find the moment of inertia about the centroidal x-axis or the centroidal y-axis, what we will do, we will again divide the small area into small area elements. Let's call this small area element as dA. Okay, and see, the centroid of the small area element is at some distance from the x-axis. Let's say, where is the center? Where is this? What is the coordinate? The coordinate. Let's suppose the coordinate, this coordinate I mean to say, let's suppose this coordinate is equal to y bar. Okay, Y bar is the y coordinate of this small area element from the centroidal x-axis. And let's call this distance as x prime. Okay, this is the distance of the centroid of the small area element from the centroidal y-axis. Okay, now we have, see, look at this y. This y is the distance of the centroid of this small area element from the x-axis. Y prime is the distance of the centroid of the small area element from the centroidal x-axis, and this x is the distance of x coordinate of the centroid of the small area element from the from this y-axis, and this x prime is the x coordinate of the centroid of the small area element from the centroidal y-axis. Therefore what we can write, if we will calculate, we can write moment of inertia I, let's take first x, moment of inertia about x-axis is equal to, the moment of inertia about x-axis is equal to integral of uh, integral of the distance of the centroid of the small element from this x-axis. That's equal to how much? Y plus y prime. That is y plus y prime square dA. Okay, this is y plus y prime square dA. Okay, now what we are actually trying to do is we had to calculate the moment of inertia of the centroid, moment of inertia of this area about the x-axis. So this is a small area element. We have to see how far is the centroid of the small area element from the x-axis, that is y plus y prime. So we write y plus y prime square, okay, because the definition is y square dA. Okay, the y coordinate of the centroid of the small area element from x-axis is y plus y prime. So this will become equal, if we, this will be, this is a plus b whole square, this will be a square, that is y square dA, that is y square, sorry, there is a little correction here, this is, this we need to correct, sorry. So I will repeat it, the moment of inertia, sorry, I will repeat it, there's a little correction, the moment of inertia about x-axis is equal to integral of the distance of the centroid of the small area element from the x-axis, that is equal to y, sorry, that's equal y square dA. Yes, this is okay, sorry. So this is equal to, as far as, let's suppose the distance between these two x-axes is, this x-axis is far away from this x-axis, let's call this distance as, let's suppose this distance is d1. Okay, this y-axis is far away from this y-axis by a distance, let's call this distance as, let's call this distance as d2. Okay, so when we write integral y square dA, this integral y square dA can be written as far as our y is concerned, y is equal to y prime plus d1. Okay, so this is y prime plus d1, y prime plus d1, and we have square dA. Now as far as this formula can be applied, this is a plus b whole square, therefore this can be written as, this is equal integral of y prime square dA plus integral of d1 square dA plus integral of twice y prime d1 and dA. Okay, this is a plus b whole square. Now look at these terms. As we look into these terms, as far as this y prime square dA is concerned, the y prime is the distance of the centroid of the small area element from the centroidal x-axis. Okay, therefore as far as this term y prime square dA is concerned, this represents the moment of inertia about the centroidal x-axis. This represents the moment of inertia about the centroidal x-axis. Okay, because if we are asked to calculate the moment of inertia about the centroidal x-axis, that will be equal to integral y prime square dA. Okay, this is the moment of inertia about the centroidal x-axis, plus, as far as d1 is concerned, that is constant. This is the distance between the x-axis and the centroidal x-axis. This will come out of integration. Left will be integral dA, that is the total. Integral dA is the total area. So it will be ad1 square. Now as far as this term is concerned, from this term, we can get our d1 is constant, 2 is constant. It will be 2 d1 integral y prime dA. Now what is this y prime dA? Okay, if we are asked to calculate the y coordinate of the centroid, the y coordinate of the centroid we can write as y coordinate of the centroid will be equal to integral 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 uh, y prime dA divided by integral dA. Okay, if we have to calculate the y coordinate of the centroid, okay, y coordinate of the centroid from the centroidal x-axis, then this formula we'll be using. But as far as the y coordinate of the centroid is concerned, where is the centroid? If you measure from the centroidal x-axis, that is at the origin. Okay, centroid is here. If we measure the centroid from the centroidal x-axis, that is lies at the origin. That is the y coordinate of the centroid as measured from the centroidal x-axis is 0. If you cross multiply, you will get integral y prime dA becomes equal to 0. Therefore, as far as this term is concerned, integral y prime dA is concerned, this term is equal to 0. So finally what we get, we'll get Ix moment of inertia, Ix about any axis is equal to moment of inertia about the centroidal x-axis plus area times the square of distance, area times the square of distance between the two x-axes. That is, we can wind it up like this. We can say, if we have to find out, if we have moment of inertia, if we have x-axis and the centroidal x-axis, if we are given that the moment of inertia about any x-axis is Ix, okay, and the distance between the x-axis and then x-axis passing through the centroid, that's called a centroidal axis, and the distance between these two axes is, say for example, d1. Okay, what will be the moment of, what is the relationship between the moment of inertia about the centroidal x-axis and any other x-axis parallel to the centroidal x-axis? Okay, the formula that we have, the relation that we have, that moment of inertia, the moment of inertia about this axis, about x-axis, is equal to the moment of inertia about the centroidal x-axis. Okay, the moment of inertia about this axis, centroidal about this x-axis, is equal to the moment of inertia about this axis, centroidal x-axis, plus area of the plane, area times the square of distance between these two, that is a times d1 square. This is the formula that is used. This formula is called the parallel axis theorem for moment of inertia. In the same way, look into this diagram. The distance between the two y-axis is given as dx. Therefore, we can write the moment of inertia about y-axis is equal to the moment of inertia about the centroidal y-axis, that is I y c or iy prime, plus total area of the plane, that is a, and square of the distance between these two, that is dx square. Okay, this is called the concept of, this is the parallel axis theorem. Moment of inertia about any y-axis is equal to the moment of inertia about the centroidal y-axis plus area times the square of distance between the two y-axis. Okay, this is how we actually do it. This is what the parallel axis theorem states. As far as the total moment of inertia is concerned, apart from the moment of inertia, so we have, like, if we are asked what moment of inertia is equal to, we have been writing this as it's equal to integral x square d or integral y square dA. Okay, so it's equal to x square dA. If the units of x are in meter, okay, then x square unit will be meter square, and we know the unit of area is also meter square. Okay, therefore the unit of moment of inertia is meter raised power 4. In SI system, the units of the moment of inertia are meter raised power 4, it are inch raised power 4, the units are feet raised power 4, so on and so forth. So units of distance raised to power 4 are actually the units of the moment of inertia. So this is moment of inertia and the parallel axis theorem. We have one more property of the area, you know, centroid of the area, moment of inertia, the product of inertia. These are called the properties of the area. Okay, we have one more property of the area, that is what we call as the we call that as the product of the area. If we will finish the product of the area, then we will go ahead with the what we call as the some numerical problems. As far as the product of the area is concerned, let's suppose we again have some area. Okay, its total area is A. We denote this to be our x-axis, and let's suppose this is our y-axis. Let's suppose the centroid of this area lies at the center, lies at the point C. Okay, pass an x-axis through the centroid parallel to the x-axis. We'll be calling this as, this is our centroidal x-axis. Okay, we'll be calling this as centroidal x-axis. This is centroidal x-axis. Okay, and an axis passing through the centroid and parallel to the y-axis, we just call this as centroidal y-axis. Okay, let's call this as centroidal y-axis. Okay, so this is what is called centroidal y-axis. Now we have area. Okay, and this area lies in the xy coordinate. We have centroid C. The x-axis passing through the centroid is called the centroidal x-axis, and the next axis y-axis passing through the centroid is called centroidal y-axis. Let's say we define the product of inertia. Okay, what we have this is our x-axis, this is y-axis, and x-axis passing through the centroid is centroidal x-axis, it's parallel to x-axis, and another axis parallel to y-axis passing through a centroid, you call it centroidal y-axis. Take a small area element dA. Okay, take a small area element dA, and suppose the centroid of this small area element dA is at a distance y prime from the x-axis and x prime from the y-axis. Okay, then we have a property of the area, what's called the product of the area, product of inertia. We define the product of inertia is defined as Ixy is equal to integral the how far the centroid of the small area element is from the x-axis, let's call that as y. How far the centroid of the small area element is at a distance is from y-axis, that is x. Then we define the product of inertia as integral x into y into dA. Okay, this is what we call as the product of inertia. Okay, this is called the product of inertia. I'm again repeating, as far as the product of inertia is concerned, the product of inertia is the property of the area. Let's suppose we have some geometrical area. Let's suppose we have some area, and this area lies in the xy coordinate system such that we select a small area element dA such that the centroid of the small area is at a distance y from the x-axis and it is at a distance x from the y-axis. Okay, then we define the product of inertia Ixy as, the product of inertia Ixy is defined as integral of x into y and dA. This is called the product of inertia. Okay, so x coordinate of the centroid of the small area element multiplied by the y coordinate of the centroid of the small area element, its integration over the area. This is called the product of inertia. This property is called the product of inertia. Now we again have, like we had the we had what we call as, we had the moment of inertia Ix or Iy, which we were writing as integral of Ix, we were writing as integral of y square dA, and we were writing Iy as, and Iy we were writing as integral of x square dA. Okay, this is how we have been writing it, integral of x square dA. Now the question is, we have already explored the parallaxis theorem for the moment of inertia, where we have been writing Ix is equal to moment of inertia about any x-axis is equal to the moment of inertia about the centroidal x-axis plus area times the square of distance between the two axes. Okay, this is what we have called the parallaxis theorem. As we have the parallaxis theorem for the moment of inertia, in the same way we also have the parallaxis theorem for the product of inertia. What is the parallaxis theorem for the product of inertia? The parallaxis theorem for the product of inertia is, again, the way we have done it for moment of inertia, in the same way we will do it for the product of inertia. Let's suppose we have an area. Okay, its total area is, say for example, A. Okay, we locate this area in x-axis, this is our x-axis, xy coordinate system, this is y-axis, and let's suppose the centroid of this area is at a point C. Pass an axis through x-axis, call this as centroidal x-axis. Pass an axis parallel to y-axis through the centroid, we call that as centroidal y-axis. Okay, so we have centroidal x-axis and we have centroidal y-axis. Now the question is, we can say how far how the distance between these two axes is, say for example, this is given to us. Let's suppose this distance is dy, or you can also write this as d1 or d2, whatever you like. And let's suppose the distance between these two y-axis, parallel y-axis, is, say for example, dx. Okay, we locate a small area element dA, okay, such that this small centroid of this small area element is at a distance y prime from the centroidal xy system, and its distance centroid of the small area element is at a distance x prime from the centroidal y-axis. Therefore, we can write the product of inertia. We can write the product of inertia can be written as, we can write Ixy, the product of inertia is equal to integral of, we are calculating the product of inertia with respect to this xy system. Okay, so let's suppose the centroid is at a distance y from this x-axis, and it is at a distance x from this y-axis. So we can write this as product of inertia by definition is integral xy into dA, which can further be written as integral of, what is x? We can write this x as, x is equal to, this total x is equal to dx plus x prime. So we can write this as, this is dx plus x prime. Okay, multiplied by this y. As far as y is concerned, our y is equal to dy plus y prime, that is dy plus y prime. Okay, and we have to take the integration over the area. We write this as dA. Now we can further simplify this. This can be simplified as, you can write this as, this is equal to integral of cross multiply, this is dx into dy, this is integral dx dy over dA plus integral of dy prime dx dA plus x prime dy dA, integral of x prime dy dA plus last one will be integral of x prime y prime dA. Okay, this is how it will go, x prime y prime into dA. That means we can further simplify this as far as we can write this as, this was our product of inertia. We are calculating the product of inertia about xy system. That is equal, dx and dy is constant, it will come out of integration. Then we have integral dA, that is total area. So it is a multiplied by dx into dy plus, let me use these two terms. Uh, let me use the term of uh, what we call as, let's use this term. Okay, this is x prime y prime dA. So as far as this x prime y prime dA is concerned, we have x prime y prime into dA, integral of x prime y prime dA. This is the moment of inertia about the centroidal xy system. Okay, this is the moment of inertia. The way we have the moment of inertia about xy system is integral xy dA. The moment of inertia about the centroidal xy system will be x prime integral x prime y prime dA. That is here, integral x prime y prime. This is the moment of product of inertia about the, this is the product of inertia about the centroidal xy system. Okay, now we are left, we have taken this term, we have taken this term. Now we are left with these two terms. So we have first have integral of, we have integral of y prime dx dA. Dx is constant, it will come out. It is the distance between the two y-axis. So we have y prime dA. What is this y prime dA equal? As far as this y prime dA is equal to, you know, where is the centroid? The centroid lies here. Okay, what is the y coordinate of the centroid as measured from the centroidal x-axis? It is 0. As in the previous case, we write the y coordinate of the centroid as measured from the centroidal x-axis is equal to integral of y prime dA divided by integral dA. But we know our centroid lies at the center of this x prime y prime system. The y coordinate is equal to 0, therefore y prime dA is equal to 0. That is, this term is 0. In the same way, x coordinate is also 0 because our centroid lies at the x0, y0. Therefore, this term is also equal to 0. What we obtain now, the moment of inertia, the formula that we have obtained is the moment of inertia. the moment of product of inertia, sorry, the formula that we have obtained is the product of inertia about xy system, okay, is equal to the product of inertia about x prime y prime system. The product of inertia about x y system is equal to the product of inertia about x prime y prime system plus area multiplied by the distances between the x and the y axis. That is, the moment of product of inertia about xy system is equal to the product of inertia about xcyc, centroidal x and centroidal y axis, plus area times the distance between the x and y axis, that is a dx into dy. Okay, this is called the parallel axis theorem for the product of inertia. So what we have, what properties we have defined till now? We have defined the moment of inertia ix and iy. Okay, we have defined ix and iy. We have defined the property like product of inertia ixy, and we have defined the parallel axis theorem for the moment of inertia and the parallel axis theorem for the product of inertia. In the next class, we'll be solving few questions. So we end up today.